Hey everyone! So, we're going to take a look at a piece of technology you use dozens of times a day, probably without even thinking about it. I'm talking about everything from your grocery list to your social media feed. On the surface, it seems so simple, but it's actually built on a total stroke of genius. I mean, think about it. You use these things constantly, right? Python lists, your to-do app on your phone, a music playlist. You add something, you remove something else, and it just works. But have you ever stopped to wonder how the computer is actually handling a list that needs to change its size from one second to the next? It turns out this super common feature is hiding a really brilliant solution to a surprisingly tricky problem. So, let's go on a little quest, shall we? Our mission is to figure out the perfect way to store a bunch of items in a computer's memory, especially when we have no clue how many items we're going to end up with. This isn't just a random puzzle, it's one of the fundamental challenges in all of computer science. And the how of this problem, the way we choose to organize everything, is what we call a data structure. It's basically the blueprint for our container. Our quest is going to start by looking at a couple of the first attempts to solve this, just so we can see where they shine and where they completely fall apart. Okay, so our first and most obvious idea is something called a static array. It's the simplest approach you could possibly imagine. And you know what? In some ways, it's incredibly powerful. But it has one single devastating weakness. The best way to picture a static array is to think of an egg carton, or maybe a bookshelf that only has a fixed number of slots. In a computer's memory, this means we ask for one single, continuous block of space. If we want to store 12 things, we get exactly 12 slots, all lined up right next to each other. No more and no less. Now, this structure has a huge advantage. Because all the slots are in one predictable row, the computer can jump to any item instantly. You want the 7th item? Bam, it's right there. It is unbelievably fast. But that fixed size? Oh, that is a glaring, massive problem. What happens when you need to put a 13th egg in your 12-slot egg carton? Well, it's a total disaster, that's what. To add just one more item, we have to find a completely new, bigger spot in memory. Then we have to copy every single item, one by one, from the old array over to the new one. And only then can we get rid of the original. This is so inefficient and so slow, especially if your lists are big. Okay, so clearly that fixed size thing with the static array is a complete deal breaker. So our next idea, the linked list, is a direct reaction against that. The thinking goes, what if we didn't need all our items to be neighbors in memory? A linked list is kind of like a treasure hunt. Each item, which we call a node, holds two things: the piece of data you actually care about and a pointer. Think of it like a clue that tells the computer exactly where to find the very next item in the list. This means our items can be scattered all over the computer's memory. And this gives us amazing flexibility. Adding a new item is a piece of cake. We just create a new node anywhere we want and update one little clue to point to it. But in gaining all this flexibility, we've lost something absolutely crucial, that super fast access we loved before. See, with a linked list, there are no shortcuts. If you want to find the 10th item, you have no choice but to start at the very first one and then follow 9 pointers, one after the other, just to get there. Imagine doing that for a list with 1,000,000 items. It would be agonizingly slow. So we seem to be stuck, right? We can have fast access or a flexible size, but it seems like we can't have both. Or can we? And this brings us to the dynamic array. This is the elegant solution that powers pretty much all the lists you use every day. It's an absolutely ingenious hack that combines the raw speed of an array with the flexibility of a linked list. The core idea here is so simple, it's profound. We're going to use an array, but we're going to relax one key rule. The size of our container doesn't have to be exactly the same as the number of items we're storing. What if our array was just a little bigger than we needed at the moment? And that's exactly how it works. We use an array, which gives us that lightning-fast access, but we intentionally ask for some extra empty space at the end. Now, when we want to add a new item, most of the time, we just pop it into the next empty slot. Done. It's an incredibly fast, simple operation. But this brings up the million-dollar question, doesn't it? That extra space is great, but it's not infinite. What happens when we finally run out? This, my friends, is where the real genius, the secret sauce of the dynamic array, comes into play. So we've filled up all our empty slots. Are we back to square one? Do we have to go through that painful, slow copy and move process all over again, just like with the old static array? The answer is Yes. But, and this is a huge but, with a very clever twist. Here it is, the aha moment. When we run out of space, we do copy everything to a new, larger array. But we don't just add a few extra slots for good measure. No, we make the new array twice as big. This geometric exponential growth is the key to the entire system. Let's just watch this in action, and you'll see why that doubling trick is so powerful. We start with a small array. Let's say it has a capacity of 4, and we fill it up. 1, 2, 3, 4. The second we need a fifth slot, boom, we trigger a resize. But we don't go to capacity 5. We double the whole thing to 8. And just like that, we have 4 fresh, empty slots to play with before we even have to think about this again. So we fill those up. And the next resize? Even more dramatic. We double it again, jumping all the way to a capacity of 16. We just bought ourselves 8 more additions that are going to be super fast. And then to 32. You see the pattern here? The amount of breathing room we create for ourselves grows exponentially. And this means those expensive, slow resizing operations get rarer and rarer and rarer as the list gets bigger. And that is the secret to its incredible average performance. This concept actually has a fancy name, amortization. And yeah, a single resize operation is very slow, we're not denying that. But because it happens so infrequently, we can spread its cost out over all the many super fast additions that came right before it. So on average, the cost of adding an item stays incredibly low. So let's look at the final scorecard. The dynamic array really does give us the best of both worlds. We get that super fast item access from the static array, and we combine it with fast add and delete performance, all thanks to that brilliant little amortized resizing trick. So that simple list you use every single day, it's powered by a really beautiful piece of algorithmic thinking. It's a perfect balancing act of trade-offs, designed to be fast on average. And it just makes you wonder, right? What other elegant solutions are hiding in plain sight in the technology we use every day? Thanks for joining me.